Chapter 5, it is now time for us to examine the engineering work required to analyze and evaluate the characteristics of a petroleum reservoir. In talking about hydrocarbon reservoirs, I'll explain some terms and definitions that will help us understand the scientific principles of how reservoirs are produced, and then describe the fluid systems and their characteristics. Next, we'll examine the different types of reservoir recoveries and the drives that are used to bring hydrocarbons to the surface. We will end by defining oil reservoirs, describing how they are calculated, and explaining their significance in predicting future production. Let's begin by describing what a reservoir is. If you recall from Chapter 2, a reservoir holds fluid that is trapped underground in porous, permeable rock. To review, porous rock is rock with microscopic holes where fluid can accumulate, and permeable rock is rock with channels that connect the holes, allowing the accumulated fluid to flow. As you learned in science, a fluid is defined as a substance that changes its shape to whatever container it's in. When we talk about a fluid in a reservoir, it can be either a gas or a liquid. Both meet the definition of a fluid. There are three basic fluids that accumulate in porous, permeable rock. They are water, oil, and gas. Obviously, the two fluids we are interested in are the hydrocarbon gases and the hydrocarbon oils, but unfortunately they are found in commercial quantities in only about 1% of underground reservoirs throughout the world. It is the task of the geoscientists and the petroleum engineers to find that 1% of 1% as efficiently and as cheaply as possible. To do that, they must have a thorough understanding of the Earth's formation, its structures, and the history of its geological features and how they changed over time. They must also be able to apply sound scientific principles pertaining to heat, pressure, and the flow of fluid within a reservoir. Before proceeding, it is imperative that we define some terms and definitions that are fundamental to comprehending the scientific principles operating in a producing hydrocarbon zone. We refer to these terms as reservoir fluid definitions. Let's start with the term fluid. As I just said, a fluid is a substance that flows and yields to any force tending to change its shape. This means that it takes the shape of its container. Both liquids and gases are fluids. Petroleum gas is defined as a substance in a gaseous state at normal atmospheric conditions, usually defined as 60 degrees Fahrenheit or 25 degrees Celsius and 14.7 psi, pounds per square inch. Now, we need to know how to measure the density of hydrocarbon fluids and understand the significance of these measurements. Remember, density is measured by dividing the weight by its volume. To begin, the measurement of density is defined by the American Petroleum Institute, API, and fixes the specific gravity for water at 1 gram per centimeter cubed. This standard allows us to compare the relative weight of crude oil to the weight of an equal volume of water. In calculating API gravity in the laboratory, we use the formula API equals 141.5 divided by the specific gravity minus 131.5. For instance, if a cubic centimeter of water is 1, we subtract 131.5 from 141.5. Because API gravity is expressed in degrees, we therefore say that the API for water is 10 degrees. Numbers greater than API gravity 10 degrees indicate that the hydrocarbons are lighter than water, and numbers lower mean that the hydrocarbon is heavier. Most oils have a higher API gravity, meaning they are lighter than water, and that is why oil usually floats on top of water. There are, however, a few oils that are heavier than water. We'll discuss them later. Now, let's look at solution gas. Solution gas is gas that has been converted into a liquid after pressure has been applied. For example, you'll find solution gas in any capped, bottled soft drink. Called soda pop in the US or fizzy drinks in the UK, these popular drinks contain solution gas. Once you remove the top and the pressure is released, the gas solution bubbles to the top. It reverts back to a gaseous state and escapes. The same thing happens in a reservoir. Under pressure and trapped in a confined space, hydrocarbon gas converts into solution gas and is dissolved in with the larger liquefied hydrocarbon molecules we call oil. When we drill an oil well, we release some of the reservoir pressure and solution gas will move to the surface, changing its state to a gas. Another term is critical saturation. This refers to the minimum saturation of oil, gas, and water in a reservoir where the molecules are connected in such a way that they create a continuous medium. This medium allows the oil or water to flow to the surface. Let's take a few minutes to review what was said in Chapter 2. There, I showed you a hypothetical well and asked if, after drilling a well, whether only water would flow or whether both oil and water would flow. At that time, I explained that for oil to flow, it has to make up at least 25% of the fluid. Otherwise, only water would flow. This exact percentage where oil will flow is known as critical saturation. Since every reservoir is a little different, we need to determine critical saturation for our particular reservoir. We do that by measuring the API gravity and viscosity of oil samples in the laboratory. The bubble point pressure is the exact pressure point when the solution gas phase reverts back to a gas phase. As pressure is released, like opening a soft drink, the bubble appears in the gas solution. It is this pressure point that is known as the bubble point pressure. Theoretically, if there's no gas in a reservoir, they say that this reservoir is above the bubble point pressure. The reverse of the bubble point pressure, where gas goes back into a liquid, is called the dew point. A detailed study of bubble point pressure and dew point pressure for different oil types are measured in laboratories. This is referred to as PVT studies. The gas cap is a layer of gas that sits at the top of the reservoir after bubble point pressure has been reached. By decreasing reservoir pressure below the bubble point, more gas is released into the gas cap. By increasing reservoir pressure below the bubble point, more gas is forced back into the gas solution. The next important term is really two definitions: associated gas and non-associated gas. Associated gas means this gas is found where black oil is present. Non-associated means that only gas is present. In these reservoirs without black oil, non-associated gas was formed in deeper formations where the source rock was usually at a higher temperature, causing the organic material to become overcooked, forming smaller gas molecules. We've talked about this next term, viscosity, in Chapter 2. As you recall, viscosity is the word used to define a fluid's resistance to flow. Its symbol is mu. For example, water flows at a faster rate than honey, so you can say that water has a lower viscosity than honey. In the oil industry, viscosity is measured in centipoise, CP. Another important term is condensate. Condensate refers to gas that turns into a liquid form when it is brought to a cooler surface, like beads of water condensing on your mirror after a hot, steamy shower. Now, the next one is the formation volume factor. When crude oil travels from formation pressure to surface pressure, the existing solution gas converts to gas and is released, causing the volume of most oils to shrink. This shrinkage is called the formation volume factor, and its symbol is beta when it is brought to the surface. For example, a barrel of oil in the formation is usually larger than a barrel of oil at the surface. It is the fraction of the space occupied by a reservoir barrel of oil to the space occupied by a stock tank barrel, STB, of oil at standard surface temperature and pressure. STB is defined as standard surface pressure at 14.7 psi and standard surface temperature of 60 degrees Fahrenheit. The formula for the formation volume factor is beta equals the volume of oil at reservoir conditions divided by the volume of oil at stock tank barrel conditions. Beta in the reservoir is usually greater than 1. Our next term is the gas-oil ratio, GOR. Here, the volume of gas is divided by the volume of oil. Keep in mind, however, that the volume of gas is measured in standard cubic feet, or SCF, while the volume of oil is measured in stock tank barrels, or STB. The formula is GOR equals SCF divided by STB. Both SCF and STB are measured at standard surface conditions, 14.7 psi at 60 degrees Fahrenheit. As the GOR goes up, there is more gas, and as it goes down, there is more oil. For example, on the first day of production of an oil well, we measured the GOR. It is 42. This means there are 42 standard cubic feet of gas for every standard tank barrel of oil. During production, these ratios are monitored closely. The GOR is represented by the following symbols. RS equals the initial reservoir GOR condition. R equals the producing GOR over time. One last definition is called the recovery factor, or RF. As you know, our present technology does not allow us to produce every molecule of oil and gas in a reservoir. No matter what we do, we can only produce a percentage of what is there. If the reservoir contains an estimated 1 million barrels of oil, or original oil in place, OOIP, and our RF, or recovery factor, is 37%, then we estimate that we can produce 370,000 barrels of that 1 million barrels of oil. This is called our RF. Later in this lecture, we will discuss ways to calculate the size of the reservoir, the OOIP, and then calculate the amount of the recoverable oil we can expect.